effect of roof was. It was not known until experiment that surface roughness had an effect on frictional distance. It turns out that the effect of negligible for laminar pipe flow, so we can write effect roof was is negligible for laminar flow pipe flow, and all laminar formulas derived in previous section are valid for the roof wall also. But turbulent flow is strongly affected by roughness. For turbulence flow, strongly affected from roughness. Consider this picture for in this picture the linear viscous sublayer extends out only to y plus equals to the y plus equals to 5. Thus, compared with the diameter, the sublayer thickness by S is only the relation for example, in this formula, if we have the relation for the quantities for Reynolds T equals to the N F a wall roughness of the about will break up the sublayer and profoundly change the wall law in this picture. Measurement of the velocity function uy in turbulent roughness wall flow. The Prandtl students Nicorats show as the figure here that, as I said, measurement of the in turbulent roof wall flow by Prandtl's student Nicorats show in this picture here, picture A. Show that a roughness height epsilon will force the logarithm law profile outward on the axis by an amount approximately equals to the ln epsilon plus as shown here, which is equals to ln. We have relation called epsilon. The slope of logarithm law remains the same, but the shift outward caused the constant b to be less by an amount of delta b equals to the Nicorad simulates roughness by gluing uniform sand grain into the inner wall of this pipe. He then measured the pressure drops and flow rates and correlated friction factor versus Reynolds number in the picture provided here. You can see that laminar friction is unaffected. In this case, but turbulent friction after on one onset point, this point, increase monotonically with the roughness ratio in epsilon on D, which shows here. For any given epsilon on D, the friction factor becomes constant, fully rough. At high Reynolds numbers, the point of change at certain values for epsilon can be listed here. For 1, in the case of we can hydraulically smooth walls. Suppose that we have hydraulically smooth walls. On new (17 and 5) transitional roughness moderate Reynolds numbers, no effect. Moderate Reynolds number effect. And the last one, which is fully rough flow. Sublayer totally broken up and friction independent. Totally broken up and friction independent of rate. Independent of Reynolds this area. The slope is for values epsilon on D. For fully roof flow, as we said, epsilon for epsilon plus greater than 70 fully roof flow, the log downshift delta B can be calculated from this relation, and the logarithmic, let me write, for fully roof flow. And the logarithm law modified for roofness plus B minus delta B which is the logarithm law modified with roofness. The viscosity vanishes, and here fully roof flow is independent of Reynolds number. If we integrated from this relation, we can obtain a average velocity in the pipe as this relation. Let me write average velocity in the pipe, which is V on U star equals to the Ln D on epsilon or we can write as a function of friction factor epsilon on D for fully roof There is no Reynolds number effect, hence the head loss varies exactly as the square of the velocity in this case. Some numerical values of friction factor may be listed. For example, for values epsilon on D, the specification of the wall, and friction factor we have, for example, for and then at the end the friction factor increases by 9 times as the roughness increases by a factor of 5,000. In the transitional roughness region and grain, we have somewhat differently from the commercially rough parts. The next chart, important chart in the pipe flow, is the Moody chart. In 19, to cover the transitionally roof range, color block combined smooth wall and fully roofed, so smooth wall and fully roofed relation ratio in a clever interpolation formula as logarithm of this is the accepted design formula for turbulent friction. It was plotted also in diagrams as Moody diagram with by Moody in the 20th century as this picture. Let me provide a picture here, which called the Moody chart for pipe friction. Moody chart for pipe friction. The Moody chart is probably the most famous and useful figure in fluid mechanics. It is accurate to about accuracy. Percent for design calculation over the full range shown in this picture. It can be used for circular and non-circular pipe flows and for open channel flows also. Open channel will be described in chapter 10. The data can be even be adopted as an approximation to boundary layer flows in chapter 7. Boundary layer on immersed, for example, bodies. The previous equation for friction factor and Reynolds number relation is comparison to evaluate for F as friction and Reynolds as D if known. Also, it is easily used to some software EES, for example. Equation solver. An alternative explicit formula given by Holland as their relation. Logarithmic Reynolds D plus which varies only 2% from previous equation, which provide here for Reynolds number. Let me provide the relation. this relation. And our new relation is 2% change in the formulation. There are various roughness values for commercial ducts available in the tables in the reference. The shaded area in the Moody chart indicates the range where transition from laminar to turbulent flow occurs. Let me show the shaded areas here. These rectangular squares. There are no reliable friction factor in this range. For no reliable friction factor, the range, let me write, Reynolds painting, and 2000. Notice that the roughness curves are nearly horizontal in the fully roofed regime to the right of the dashed line. From test with commercial pipe, recommended value for average wall roughness listed in the table 6.1 in the reference. Round pipe fluid mechanics.